In this video, I will explain transmission line equations. Transmission line equations. A two-conductor transmission line supports a TEM wave, that is, electric and magnetic fields on the line are transferred to the direction of wave propagation. Important point here is a two-conductor transmission line supports a TEM wave. That is the electric and the magnetic field fields on the line are transfers to the direction of wave propagation. TEM wave transfers electric and magnetic fields. Both are perpendicular to each other in the direction of wave propagation. Another important property of the TEM wave is that the fields E and H are uniquely related to voltage V and current I. Another important property of TEM wave is that the fields E bar and H bar are uniquely related to voltage V and current I respectively. V and I are the circuit quantities. V is related to electric field minus line integral E dot dl. This is voltage relation to that electric field, and current relation integral over H dot dl. V is related to electric field, I is related to magnetic field. Instead of E and H, we use circuit quantities, voltage and currents in solving transmission line problems. We will use circuit quantities V and I in solving field quantities, we will use the circuit quantities V and I in solving transmission line problems. Transmission line problems instead of solving field quantities. To quantities E and H, E bar and H bar. The circuit model is more simple and convenient than analysis of E and H fields. The circuit model is the circuit model is simpler and more convenient Instead of electric field and magnetic field analysis, we use V and I elements. These are the circuit quantities. Analysis of circuit quantities for solving transmission problems instead of E and H is simple one compared to analysis of E and H fields. To understand transmission lines, we will set up an equivalent circuit. To understand transmission lines, we will set up an equivalent circuit. To model and analyze them. We will set up an equivalent circuit. To start, we will take a basic symbol for a transmission line of length L and divide it into small lengths. To start, we will take the basic symbol for a transmission line of length L, capital L, and divided into a small and divided into small segments shown in below. This is the two conductors are shown in figure. Parallel wires representation. This one is a parallel wire representation. The each length of the parallel wire is capital L. This transmission line of length L is divided into small segments shown in figure, divided into small sections of length dz. Divided into small sections of length dz. Shown in figure. Divided into small sections of length dz. Then we model each small segment with a small series resistance, series inductance, shunt conductance, and shunt capacitance. These are the primary constants of the transmission line. Then individually model each segment into primary constants. Then we will model each small segment, with a small series resistance, the small series resistance, series inductance, the small resistance is due to cross-sectional area of the conductor. That is, transmission line is a conductor. Next, small series inductance. Series inductance is due to a current flow through the conductor develops some magnetic field. That magnetic field is analyzed with the help of that series inductance. Next one, shunt conductance. Shunt conductance. These are the two parallel wire conductors. An air acts as a dielectric between these two parallel wire conductors. Some capacitance effect is also there. That is called as a shunt conductance and shunt capacitance. Shunt capacitor. These two parallel wire conductors acts as a capacitor. In between these two parallel wires, some air acts as a dielectric. Some leakage is also there between these two parallel wire conductors. The leakage, the system is analyzed with the help of shunt conductance. Each small segment, this is a small segment of this transmission line of length dz, is analyzed like that. The series resistance value is R dz. Here a small segment length dz here. Here also delta z, R delta z, and some inductance L delta z, and capacitance C delta z, and some conductance G delta z. So one is A dash, B dash. R is the resistance per unit length of the transmission line. Here R is the resistance per unit length, per unit length of the transmission line. Ohm per meter. L is the inductance per unit length, per unit length of the transmission line. Henry per meter. G is the conductance per unit length. G is the conductance per unit length. Of the transmission line. Siemens per meter. C is the capacitance per unit length for the transmission line. Farad per meter. These are the primary constants of the transmission line. These are independent of the frequency of the propagation. This is a small, consider a small segment with a small, we will model each small segment with a small series resistance, series inductance, shunt conductance, and shunt capacitance. L-type equivalent circuit model of a differential length delta Z of a two-conductor transmission line shown below. L type equivalent circuit model, of a differential length delta Z of a two conductor means two parallel wires, two parallel conductors, two conductor transmission line, shown below. This is the resistance R delta Z, L delta Z, G delta Z, C delta Z. From the generator side, this is the two generator V of Z of t, I of Z of t. This one is delta I of Z plus delta Z, incremental change of t. Here also V of Z plus delta Z of t to load. Let us examine an incremental portion of length delta Z of a two conductor transmission line. Let us examine an incremental portion of length delta Z of a two conductor transmission line. Assume that the wave propagates along the Z direction from the generator to the load. We assume that the wave propagates along the Z direction from the generator to the load. R into delta Z is the series resistance, L into delta Z is the series inductance, shunt conductance, and the shunt capacitance. At the generator end, the load voltage is represented by V of Z of t. The current coming from V of Z of t is I of Z of t. At the load side, the voltage is V of Z plus delta Z of t, I of Z plus delta Z of t. These are the equations, the L-type equivalent circuit of the transmission line. By applying Kirchhoff voltage law to the outer loop of the circuit, Kirchhoff voltage law, that means V of Z of t is equal to I of Z of t into R into delta Z plus L delta Z. The voltage across that inductance is V is equal to L into di by dt. L into di by dt. Here I is I of Z of t. L is L into delta Z. And outer loop means includes series resistance, series inductance, V of Z of t and V of Z plus delta Z of t. Apply Kirchhoff voltage law to the outer loop of the circuit. Apply KVL Kirchhoff voltage law to the outer loop of the circuit. V of Z of t is at the generator side. R into delta Z is the series resistance. The current flow through the R into delta of Z is I of Z of t. Next, inductor is there. The voltage drop across inductor is L into di by dt, L delta of Z, d by, that means dou by dou t, because we use a small incremental length of transmission line is delta Z. That is the reason we use dou by dou t of current I Z of t. At the load side, the voltage is V of Z plus delta Z of t. Here delta Z is the in both sides delta Z is there. Delta Z R I of Z of t plus L dou I of Z of t by dou t. That is equal to V of Z of t by delta Z, V of delta Z by delta Z. Here plus here one more plus V of Z plus delta Z of t. V of Z of t minus V of Z plus delta Z of t is equal to pi delta Z Ri of Z of t plus L into dou I of Z of t by dou t. We use minus sign here, minus V of Z of delta Z of t by t minus V of Z of t by delta Z is equal to R into I of Z of t, L into dou by dou t of I of Z comma t. This is the taking the limit of above equation, delta Z tends to 0 leads to taking the limit of above equation, the limit of above equation delta Z tends to 0 leads to minus limit delta Z tends to 0 V of Z plus delta Z of t minus V of Z comma t by delta Z is equal to R I Z of t plus L into dou by dou t of I of Z of t. This V of Z plus delta Z of t minus V of Z of t is the change in voltage along the Z direction. minus limit delta z tends to 0 del of v of z by delta of v of z by delta z is equal to ri z comma t plus L into di by dt. I is a function of z comma t. This can be represented as a partial derivation minus dou v of z means z comma t by dou z. The wave is propagating along z direction. Here delta z is represented by dou z. Here vz is v of dou of v of z comma t is equal to r I comma z comma r into I of z comma t plus L into dA of z comma t by dt. This is the equation 1. Similarly, applying Kirchhoff current law to the main node of the circuit. Similarly, applying Kirchhoff's current law to the main node of the circuit. See the circuit diagram here. Main node is here, this one. I of z of t is the current entering into this node. Delta I is the current away from the node. I of z plus delta z of t is the current leave the node. Therefore, I of z of t is equal to delta I plus I of z plus delta z of t. This is the KCL equation at the main point. I of z comma t is equal to I of z plus delta z of t plus delta I. Here I of delta I of z plus delta z of t. Here g of delta z and c of delta z is there. The current is delta I. Here the voltage is V of z plus delta z of t. Therefore, delta I is the combination of two currents. That is V delta z, G delta z into this V gives rise to current flow through this conductance. Conductance into voltage. I is equal to Y into V. Y is G into delta Z. V is V of Z plus delta Z of T. And similarly, I is equal to C into dV by dt. C is C into delta Z. V is the V of Z plus delta Z of T. Write this one here. Delta I is divided into two currents, that is Ix and Iy. This one is Ix, this one is Iy. Ix plus Iy, that is equal to I of Z plus delta Z of T. Ix is G into delta Z. V of Z plus delta Z of T plus Iy is equal to Iy, C into dV by dt. C means C into delta Z, d by dt. V is V plus Z plus delta Z of t. Here I of Z comma t minus I of z plus delta z of t. Delta z is common term, g into v of z plus delta z of t plus c into d by not dou by dou t, here dou v of z plus delta z of t. Here we use minus sign. I of z plus delta z of t minus I of z comma t by delta z is equal to g into v of z plus delta z of t plus c into dou v of z of delta z of t by dou t. As a limit taking the delta z tends to 0 in the above equation, we use the limit minus limit delta z tends to 0 I of z plus delta z of t minus I of z comma t by delta z is equal to g into v of z plus delta z of t c into dou by dou t v of z plus delta z of t. Here change in current is represented by minus limit delta z tends to 0 delta of I of z by delta z is equal to g into v of z plus delta z of t c into dou by dou t of v of z plus delta z of t. This can be represented as a partial derivation. Dou minus dou of dou into I of z of t by dou z is equal to g into v of z plus delta z of t plus c into d by dou t v of z plus delta z of t. Here delta z tends to 0, delta z tends to 0, this value is 0, this value is also 0. Therefore finally minus dou of dou into I of z comma t by dou z is equal to g into v of z comma t plus c into dou by dou t v of z comma t, because delta z is equal to 0. This is the equation number 2. Using a phasor form, using a phasor form. Phasor form means v of z comma t is equal to a real term of vs of z at the source side e power j omega t. I of z comma t is the current at the source side, generator side, not load side. A real term of is of z into e power j omega t. Consider equation 1. This is the equation 1 and the equation 2. Convert this time domain equation into, this is the time domain equation, this one is phasor form. This is the relationship between these two. Convert this time domain equation into phasor domain. Minus first equation is dou of v of z comma t by dou z is equal to r into I of z comma t L into dou I of z comma t by dou t. This is the equation 1. Substitute equation. This is the phasor relation between a time domain and phasor form. Minus dou of v of z of t is equal to a real term of vs of z e power j omega t by dou z I of z comma t. I of z comma t is here I of z comma t is real of is of z e power j omega t plus L into dou by dou t of real of is of z e power j omega t minus real of dou by dou t vs of z e power j omega t is equal to r into real of is of z e power j omega t plus L into dou by dou t. That means real of is of z derivative of e power j omega t is e power j omega t. J omega t derivative is, that means j omega. Minus real term of dou by dou t is dou by dou t. Dou by dou t real term is vs of z e power j omega t means cos omega t plus j sin omega t. Real term is cos omega t. R into real of is of z e power j omega t is is of z cos omega t plus L j omega. Real of is of z e power j omega t is is of z cos omega t. Is of z cos omega t. That is equal to cos omega t, cos omega t, cos omega t is cancelled. Minus dou by dou t vs of z is equal to r into is of z. This cos omega t is also cancelled. J omega L is of z. J omega L is of z. That is equal to minus dou vs of z by dou t. Not dou t here. Not dou t here. Dou z. Here dou z. This is the dou z. Dou z here. Dou z. Dou z. Dou z. R plus j omega L. R plus j omega L into is of z. Into is of z. This is the equation 3. Consider current I of z comma t is equal to real of is comma z is of z e power j omega t. From second equation minus dou I of z of t by dou z is equal to GV of Z of t, C into dou by dou t, V of Z of t. This is the second equation. Already the second equation is also derived. Minus dou by dou z means dou by dou z. I z of t is real of is of z e power j omega t is equal to g into v of z of t is real of vs of z e power j omega t plus c into dou by dou t of real of vs of z e power j omega t minus dou by dou z real of is of z e power j omega t is is of z cos omega t. G into real of vs of z e power j omega t is vs of z cos omega t plus c into dou by dou t real of vs of z derivative of e power j omega t is e power j omega t into j omega, that is equal to g vs of z cos omega t j omega c vs of z cos omega t, vs of z cos omega t. This one is minus cos omega t and cos omega t is cancelled. Dou of is of z by dou z is equal to g plus j omega c into vs of z. This is the equation number 4. Consider equation number 3. Minus dou of v of vs of z by dou z is equal to r plus j omega l is of z. Dou vs of z by dou z is equal to minus of r plus j omega l is of z. Differentiate this equation with respect to z. Dou square vs of z by dou z square minus r plus j omega l dou is of z by dou z. Dou is of z by dou z is minus g plus j omega c vs of z. That is equal to minus r plus j omega l minus g plus j omega c into vs of z into vs of z. Minus minus is cancelled, minus into minus plus, therefore r plus j omega l g plus j omega c vs of z dou square vs of z by dou z square. This one is gamma square vs of z dou square vs of z by dou z square. gamma square is equal to r plus j omega l into g plus j omega c. The entire term is stated as gamma square, propagation constant. Dou square Vs of z by dou z square minus gamma square Vs of z is equal to 0. Vs of z is equal to 0, where gamma is equal to alpha plus j beta. Alpha is the attenuation constant, beta is the phase constant, gamma is the propagation constant. R plus j omega L G plus j omega c. Similarly, we know that fourth equation dou is by dou z is equal to minus g plus j omega c Vs of z, Is of z here. Differentiate by equation with respect to z. Dou square Is of z dou z square minus g plus j omega c dou Vs of z by dou z. Dou Vs of z by dou z is r plus j omega l minus g plus j omega c minus r plus j omega l Is of z. Dou Vs of z by dou z is minus r plus j omega l Is of z. Minus minus cancel. Therefore, dou square Is of z by dou z square is equal to g plus j omega c r plus j omega l Is of z. Dou square Is of z by dou z square minus gamma square Is of z is equal to 0. Wave equation for circuit elements, that means voltage and currents, similar in form to the wave equation obtained for plane wave. For voltage, dou square Vs of z by dou z square minus gamma square Vs of z is equal to 0. For current, dou square Is of z by dou z square minus gamma square Is of z is equal to 0. This is the wave equations. Gamma square is equal to r plus j omega l g plus j omega c. Alpha is attenuation constant measured in alpha is attenuation constant, beta is the phase constant. The wavelength lambda is equal to 2 pi by beta. Velocity of the wave is v is equal to f lambda. F is f into 2 pi by beta. 2 pi f is omega by beta. This is the two equations. The two equations are dou square Vs of z by dou z square minus gamma square z is equal to 0. Dou square Is of z dou square Is of z by dou z square minus gamma square z into Vs of z. Minus gamma square Vs of z is equal to 0. Here gamma square Is of z is equal to 0. The solution of the linear homogeneous differential equation are, here Vs of z is equal to V0 plus e power minus gamma z plus V0 minus e power gamma z. Is of z is equal to I0 plus e power minus gamma z plus I0 minus e power gamma z. This is the positive plus z minus z. This one is positive z, this one is minus z, where V0 plus V0 minus I0 plus and I0 minus are wave amplitudes. The wave amplitudes, the plus and minus signs respectively. The plus and minus signs respectively denote wave traveling along plus z and minus z directions. Plus z and minus directions as indicated by an arrow. Indicated by an arrow. See the phasor form. Vs of z is phasor notation. This phasor notation is converted into a time domain notation. That means v of z comma t. Real of Vs of z phasor notation into e power j omega t. That is equal to real of Vs of z is V0 plus e power minus gamma z e power j omega t plus real of V0 minus V gamma z e power j omega t. That is equal to real of V0 plus gamma is alpha plus j beta z e power j omega t plus real of V0 minus e power gamma is alpha plus j beta z into e power j omega t. That is real of V0 plus e power minus alpha z e power minus j beta z e power j omega t. Real of V0 minus e power minus alpha z e power this one is gamma z. E power j beta z e power j omega t. In both the terms, e power minus alpha z is the common one. A real of V0 plus e power j omega t minus beta z. Real of V0 minus e power j omega t plus j beta. Bz b that is equal to e power minus alpha z real term of V0 plus e power j omega t minus beta z is V0 plus cos omega t minus beta z. Here e power alpha z is also there. E power alpha z V0 minus cos omega t plus beta z. Voltage and current at any given point on the transmission line in terms of characteristic impedance. In terms of characteristic impedance. Characteristic impedance Z0 of the line is the ratio of positively traveling voltage wave to current wave at any point on the line. The characteristic impedance Z0 of the line is the ratio of positively traveling voltage wave to current wave at any point on the line. The characteristic impedance Z0 of the line is the ratio of positively traveling voltage wave to current wave at any point on the line. That is Z0 is equal to V0 plus by I0 plus. That is equal to another definition is minus V0 minus by I0 minus. We know that Vs of Z equations Vs of Z is equal to V0 plus e power minus gamma Z V0 minus e power gamma Z. Is of Z is equal to I0 plus e power minus gamma Z plus I0 minus e power gamma Z. Dou of Vs of Z by dou Z is equal to R plus j omega L Is of Z. This is the equation. Dou by dou Z Vs of Z is V0 plus e power minus gamma Z plus V0 minus e power gamma Z is equal to R plus j omega L. Is of Z is I0 plus e power minus gamma Z I0 minus e power gamma Z. Minus V0 plus e power minus gamma z derivation with respect to dz is e power minus gamma z minus gamma V0 minus e power gamma z gamma is equal to r plus j omega l I0 plus e power minus gamma z I0 minus e power gamma z. Quotients of e power minus gamma z and e power gamma z on the two sides of the equations. The coefficients of e power minus gamma z and e power gamma z. E power minus gamma z quotient is minus into minus plus gamma V0 plus is equal to r plus j omega l I0 plus e power minus gamma z quotient. E power minus gamma z quotient is r plus j omega l into I0 plus V0 plus by I0 plus, that is the characteristic impedance of the wave, that is equal to r plus j omega l by gamma. Gamma is the propagation constant. R plus j omega l by gamma is square root of r plus j omega l into g plus j omega c. That is equal to r plus j omega l square root of r plus j omega l square root of r plus j omega l by square root of r plus j omega l into square root of g plus j omega c. Therefore, characteristic impedance of the wave Z0 is equal to square root of r plus j omega l by g plus j omega c. That is equal to V0 plus by I0 plus. This is quotients of this is the quotient of e power minus gamma z quotients. The quotients of e power gamma z, quotient of e power gamma z, that is equal to quotient of e power gamma z is in this expression minus V0 minus gamma is equal to r plus j omega l I0 minus. Gamma minus gamma V0 minus is equal to r plus j omega l I0 minus. V0 minus by I0 minus is equal to r plus j omega l by minus r plus j omega l by gamma. This is also characteristic impedance Z0. R plus j omega l, gamma is the square root of r plus j omega l into g plus j omega c. That is Z0 is equal to minus of square root of r plus j omega l by g plus j omega c. Z0 is equal to here Z0 is equal to minus V0 minus by I0 minus V0 minus by I0 minus. We know that equations, the two equations are Vs of Z is equal to V0 plus e power e minus gamma Z, V0 minus e power gamma Z. I0 of Z is equal to I0 plus e power minus gamma Z, I0 minus e power gamma Z. Characteristic impedance is the ratio of V0 plus by I0 plus V0 Z0. V0 minus I0 minus is equal to minus Z0. From this expression, I0 plus is equal to V0 plus by Z0. I0 minus is equal to minus V0 minus by Z0. These two are substituted in that expression. Therefore, I0 of Z is equal to V0 plus by Z0 e power minus gamma Z. Here I0 minus is V0 minus V0 by Z0 minus V0 minus by Z0 e power gamma Z. This is the characteristic impedance. Z0 is equal to square root of R plus j omega L by G plus j omega C. The characteristic impedance is also defined as ratio of forward voltage wave to forward current wave at any point on the line. That is equal to V0 plus by I0 plus. The characteristic impedance is also defined as negative of the ratio of reverse voltage wave to the reverse current wave at any point on the line. Z is equal to minus V0 minus by I0 minus. With this, the characteristic impedance of the transmission line is complete.